So a lot of brains, as I said, have gone into the development of this robust and comprehensive predictive performance modeling tool. Essentially, this is a tool that is capable of assessing the feasibility of electrification and decarbonization using selected technologies at your fleet. And in doing so, we consider different technology options such as battery electric buses, hydrogen fuel cell electric buses, diesel, CNG, and hybrid buses, electric low speed automated shuttles. Essentially, you have a zero emission solution that you want modeled. We can do it. And it's not simply restricted to buses alone either. Although our principal operation has been in transit, that's where the clients have been. So we have catered to our clients' needs, but we can do more like predictive performance modeling for light duty, medium duty, or heavy duty applications. And in the different technology options that you have, we can do prototypical modeling, or we can do like the currently available technology modeling as well. Fundamentally, you name it, we can do it, and we have the demonstrated capability to do it. This particular slide is talking about different functionalities or characteristics of the Rout 2.0 tool set, and I would take a few examples of what this is able to do from this particular slide here. When a transit agency or any agency wants to electrify its fleet, one of the fundamental elements that they want to see is whether or not it would be successfully implemented, whether or not they would be able to replace their currently operational diesel fleet or a fossil fuel powered fleet with the chosen technology. If it is a battery electric bus, how successful the battery electric bus would be on that given topography in that given route. And or if it is hydrogen fuel cell, what is the expectation that you would have when you actually procure and deploy a hydrogen fuel cell bus there. One of the key elements that is highlighted for Rout 2.0 modeling is we can predict the performance success rates for different zero emission buses. And in doing so, we consider the revenue as well as non-revenue operations. And the focus here is on transit, if we may for a second. The revenue operations are captured in the data set that the transit agency would have, and that's the general transit system feed data. There is also a non-revenue system or non-revenue operation that all transit agencies would need to pass through. How the operator pulls out from the garage at the start of the day up until they go and pick up their first passenger, it's a pull out non-revenue. They have a similar non-revenue distance when they actually pull back into the garage at the end of the day, that is pull back in. There would be a lot of interlining that the service requirements mandate the operator to take, which means there is interlining and deadheading involved in a particular vehicle's operation. So when Rout modeling happens, we are actually modeling the experience of your vehicles. We would be telling you these are the non-revenue or attributes associated with this vehicle operation, and these are the revenue operations. And based on a combined revenue and non-revenue operational system, we are predicting the performance of a chosen technology. It may or may not work. It may be possible for you to have a 1:1 replacement of diesel buses with battery electric buses in the chosen technology. It may not be possible for you unless you have opportunity charging. It may not be possible for you unless you have at least 2 buses to cover the same range requirements that your diesel bus has. So there are a lot of considerations like that, and we do provide very solid and detailed explanations and data to prove the case for the transit agency. We would be assessing the suitability for the route, block, or vehicles for electrification. I say that because there are different orientations that we can adopt per the demand of the client and per the requirements that they have, and per the data sophistication. It can be a route-based analysis, or it can be a block-based analysis, wherein we consider what is the applicability for a particular technology in a block, or it can be a vehicle-based analysis wherein we look at what is the 1:1 replacement potential for your diesel fleet. We do look at the actual GHG emission reductions from a tailpipe, from a life cycle perspective. I mean, compare it with fossil fuel sources. So why I say that is all of the zero emission sources that we are talking about here, battery electric or hydrogen, would not have any tailpipe emission, but that doesn't mean they are zero emission, from a full life cycle perspective. there would be like emissions depending on the cleanliness of the grid, how green the grid is that is used to power your vehicles, whether it be to produce hydrogen utilizing electrolysis or whether it be to actually charge your batteries on board your bus. So the point is we establish that economic business case as well as the environmental business case for you utilizing the predictive performance modeling tool in Rout 2.0. So now I want to get into the details of the Californian Transit Agency work here. Our GIS work is the first step of our Rout 2.0 predictive performance modeling, and it is an intense and a highly complex a set of data analysis that our GIS team does. And we start by collecting and cleaning the data. We tailor the data collected to the needs of the project. We identify different impediments and speeds for the routes. We relate and interconnect several different data sets, and that include the GTFS, as I previously mentioned, the traffic signs, the topography, the elevation, and we'll do look at the route profile as an after effect of all of this, or a result of all of this data interconnection, and then create a model that identifies the indicative route profile for each block. And in doing all of this, we do look at the non-revenue mileage, as I previously mentioned, the pull in, the pull out, the deadheading and interlining involved. We, in this particular case, created 8 generic non-revenue routes for this Californian Transit Agency, given the data set. The number of generic non-revenue routes that we create vary depending on the complexity of the data and the actual non-revenue assignment. So this is a highly complex process that we undertake in the GIS modeling, and the GIS results actually are geospatial outputs that feed into the next phase of the work, which is duty cycle generation. Before I get into the duty cycle, I do want to highlight this non-revenue mileage element, because it's a key element of CUTRIC's tool. If you do have a predictive performance done without considering non-revenue, it would be underestimating the or overestimating in some cases the performance, because you can think that your battery electric buses is capable of covering this much distance or this many blocks, but it may not realize in actual terms because of the non-revenue distances taking away from the battery. So in this particular case, as I mentioned, there were 8 non-revenue routes that were created and assigned to the revenue profiles. And we considered 137 blocks in this particular analysis, considered pull in, pull out, deadheading. And you can see the descriptive statistics on the right-hand side there. The minimum non-revenue distance that this particular transit agency in California had was around 4 kilometers. The maximum is 119 kilometers. So around 120 kilometers is spent in non-revenue, which means the agency is not collecting any revenue. The bus is running more or less empty without having any passengers on board. So all of those non-revenue distances add to the range that the bus is expected to deliver. When it is a fossil fuel powered system, we do not necessarily worry too much about non-revenue, but as soon as you make the switch to electrons, whether it be hydrogen or battery, those non-revenue distances have a very strong role to play, and hence our emphasis on this. As you can see, the bell curve of the non-revenue block assignments with the assignments from A to H. The right-hand side table shows the different route lengths that are the maximum for all of those assignments. So for example, block D, the route and non-revenue route number D has a length of 43.7 kilometers. So that is what we mean. And the bell curve shows the distribution of those 8 non-revenue assignments in our GIS work. So the geospatial outputs from the GIS modeling work, which includes non-revenue and revenue profiles, feed into our duty cycle generation work. In the duty cycle generation, we do synthetically create duty cycles based on the actual information, the speed limit data, etc., collected from the transit agency themselves. There are 4 different graphs, as you see on this particular slide here. One is the speed profile. If we start on the top left-hand side, this is the actual speed in kilometer per hour listed on the y-axis, and the simulated time in minutes on the x-axis. As you see, in the 30 minutes of simulation, this block is expected to have like a lot of acceleration and deceleration starting and stopping. As you can see, the speed comes back to 0. The maximum speed that it goes to is around the 65 kilometer per hour mark, but it stays more or less close to the 60 kilometer mark for most part. The distance profile in the same 30-minute window shows how much distance this particular block is. It's 15 kilometers in length. The elevation profile and grade profile are showing the hilliness of the terrain as well as the undulations that the road experiences respectively. So the elevation profile, as you can see, what the bus experiences, it goes from around 240 or 245 meters above sea level to almost 275. So we are looking at like a 30-meter elevation, which is not insubstantial for a battery electric bus or a hydrogen fuel cell electric bus because of the energy intensity involved. The grade profile is basically showing what your pavement looks like, what is the undulation that the vehicle would experience when they are on your particular road. In this particular case, the transit agency has a significant degree of undulation because the gradient in the grade profile is ranging from around -15 to almost +15. So that is a strong grade profile that this transit agency has in the roads, on the roads. The heavy duty cycle is basically showing an intensified profile of the medium duty. So when we talk about our duty cycles, there are 3 in number. Sometimes we add more depending on the complexity of the work and the sophistication that the client requires as well. In this particular case, there were 3 duty cycles created. There were a total of 214 blocks and 642 duty cycles that are created. And we utilized the ridership data that the transit agency provided as well. Typically, in the case of a duty cycle, it is offering a spectrum of possibilities before the client. In the case of a lighter duty cycle or a less intense duty cycle, the energy utilization would be at the bare minimum. And we are showing them the theoretical bus case scenario possible for those buses if it is moving on those particular roads. In the case of the heavy duty cycle, it's actually the intensified version, which is what you are seeing here as well in the simulated duty cycle. We would be looking at extreme energy demands placed on the battery. The HVAC is turned on full. It would be like if it's in the Californian case, it would be like AC in full swing, and the riders are full on the bus. The maximum ridership is happening, and the bus is possibly climbing up a hill. So the energy intense episode is captured in that heavy duty cycle, and the medium duty is where the average operation is going to be like. There would be some heavy duty scenarios that the transit agency experiences, but it won't be all heavy duty in most cases. It would be closer to the medium or the average duty cycle, but we offer that spectrum of possibilities discussion before them so that they can understand what it would mean to operate zero emission solutions on their fleet. So now we get into the results of this analysis. In this particular case, 2 configurations of battery electric buses were chosen by this transit agency for modeling purpose. And as you can see, the results here for 2 agencies, for one agency with 2 bus configurations. I mean, bus number A is a 400 plus kilowatt hour battery pack on board. Bus number B is a 600 plus kilowatt hour battery pack. So slightly different battery capacities on board. And you would see what it takes to actually operate these buses on Californian roads. On a typical weekday in the average duty cycle, we are looking at 1.28 kilowatt hour of energy spent per kilometer. In the case of the 600 kilowatt hour bus, the energy fuel economy that you see is 1.25 kilowatt hour per kilometer. Now, a common question that you might be wondering is the battery capacity, when it increases, it should be increasing the weight of the bus. So wouldn't the fuel efficiency be dropping? In the case of these bus comparisons, there were a lot of physical features that were different, but the weight comparison meant that bus B is lighter than bus A, which was a factor that was considered when we modeled it, and that is one of the reasons why a lower energy is spent per kilometer by bus number B. The heavy duty, as I mentioned previously, it's an energy intense scenario. You are expected to spend more energy per kilometer. Hence, the results show 1.81 kilowatt hour per kilometer for bus number A. And it is slightly lower, but very close at 1.77 kilowatt hour per kilometer for the second bus option. Now we look at the success rates for selected blocks at this particular transit agency. Here, what we see is the depot charging only. So if the bus is, having an opportunity to charge at the depot overnight and leaves the garage at the start of the day with 100% state of charge, what is the expected performance that these buses are about to have? So in the case of depot only charging, this Californian transit agency can expect around 25% success for bus number A, which means that 75% of their fleet would run out of power sometime during the service day if the electrification is done using bus A. In the case of bus B, it is actually at 72%. It's a higher number for depot only charging, and that has to do with the higher battery capacity as well. That is in the medium duty scenario. The moment you switch to heavy duty, which as I mentioned, in some cases it can happen on the service delivery days, 17% is the success rate for bus number A. For bus B, it would be 23%. So the success rate drops substantially for bus B as well. And the depot only charging results is what you see here. The criteria for determining whether or not the given bus is successful or block is successful is to see if the state of charge on the battery on board drops below 20% after completing the block. If it drops below 20%, we deem that unsuccessful. The reason for that is to maintain the longevity and the health of the battery per industry standards. We do not model situations wherein the state of charge drops below 20% because you would be ending up to replace your battery sooner than you want. So agencies also do not want to have that multiple battery replacements either. So we maintain the health of the battery. That's the reason for the 20% criteria chosen here. Now, this is the range requirements with depot only charging or range expectations that this particular transit agency can have. Bus number A, around 291 kilometer range. Bus number B, on the medium duty cycle, can be expected to cover around 423 kilometers. In the weekday scenario, for heavy duty, the range expectations need to be changed because the energy efficiency values have substantially changed as well. You would see the range drop from 423 to 298 for bus B, and similar drop for bus A from 291 to 206 kilometer. Now, as you noticed, the opportunity charging is required for this transit agency because the depot only charging does not result in like a substantial degree of success for them. So we looked at what the opportunity charging would mean for them, and similar to the depot charging, we calculated the fuel efficiency 1.28. For bus number A, 1.25 for bus number B, and we looked at what it meant for the total energy consumption, which is going to be similar for depot only charging or opportunity charging because the physical features of the vehicles are very much similar. This is enabling the transit agency to see what kind of an energy plan they would need to have and what is the amount of power that they would be drawing from the grid in terms of energy. If we look at the opportunity charging, again, the weekday results are shown here. If we estimate a 5-minute per round trip charging episode for these buses, we would notice the first graph on the right, on the left, I mean, you would notice the success rate jumping from the 25% that you saw in the depot only charging to 70% for bus number A. For bus B, it actually rose from the 70% to 94% here. This is with 5-minute per round trip charging. Same criteria for 20% state of charge is maintained here. This transit agency wanted us to see what it would mean to actually add 1 more minute to the charging episode, which is why we consider 3 minutes per single trip charging. And as you can see, 1 additional minute means a 10% increase in success rate for bus number A, 2% for bus B in the medium duty scenario. Heavy duty is also very much similar.
Parvati, if we can wrap up.
Yes, thank you, Sherwin. So quickly about fuel cell, medium duty, heavy duty results are shown. The amount of kilometers, the distance that you can cover per kilogram of hydrogen was also done as a part of this analysis, and the energy consumption is also listed here. The fuel cell analysis results are shown. The 91% is higher than what we saw in the case of battery electric buses, and the heavy duty is also having a good degree of success. We didn't consider a 1 refueling episode, but if a 1 refueling episode is done, then the success rate would go up substantially. So that is what I want to end with. Thank you so much for listening to me. If you do have questions or you do want to learn more about Root, do complete our Root inquiry form and we would be able to discuss more with you. Thank you.